So yeah, hello everyone. A very good evening. I hope I'm audible and visible. So if not, anyone of you can let me know at any point of time whether I am visible or not. Okay, so let's wait for 5 to 10 minutes so that everyone can able to join this session. Okay, hello everyone. A very good evening. I hope I'm audible and visible. Any one of you can confirm it whether I'm audible and visible. Yeah, good evening. I'm audible and visible. Okay, thank you. Thank you, Arza. So, okay, my name is Pooja Verma. I'm PMRF Research Scholar from IIT Kharagpur, and instructor for this course is Professor Santanu Chattopadhyay from Electrical and Electronics Engineering Department, IIT Kharagpur. This is a week 5 live interactive session on digital circuits. And for asking and interacting, you can use the chat box, or whether you can unmute yourself and ask your questions or doubt. Okay. Okay. So these are the some topics which have been covered for this week. So I hope all of you have gone through this week video lectures. Yeah, I am taking some one day earlier. There is some situation which have been occurred. That's why I am taking it today. So that's fine if you have not gone through these topics. So hopefully you have gone through this. These are the some topics which have been covered for this week. Okay, so first one is look ahead carry adders, then decimal adders, binary multipliers, comparative circuits, code converters, decoder, encoder, and multiplexer. Okay, okay. So moving to the questions or problems. So the first question is the number of 2:1 multiplexer required to implement 8:1 multiplexer is. So how many 2:1 multiplexers are required to implement 8:1 multiplexer? Option A is 6, option B is 7, option C is 8, and option D is 9. So anyone of you want to guess this question? Then we will solve this question. So, okay. So already we know that to implement 2 to the power n into 1 mux using 2:1 mux. The total number of 2:1 mux is required. How many 2:1 mux are required to implement 8:1 mux? If we want to convert it, so if we do 2 to the power 3, then here we will get n is equal to 3, right? That is also 8:1 multiplexers. So we can solve it in a two ways. Okay. So one way is, so if the number of 2:1 mux required to implement 8:1 mux will be n, we know that, right? Or we can say that we know that what will be the to implement what number of mux we want to implement, that is 8:1. So first is the that part minus 1. Let's see, it is k minus 1. So 8 minus 1 is 7. Other way to solve it, we need to find out at first stage how many mux are required. That means 8 divided by 2. First we have to divide 8 divided by 2. How, for which number of mux we need to implement? So at first stage you can say that 4. First stage. Okay. So at first stage how many mux we are required? 4. and in the second stage now we have to divide by 2. So 2. So at second stage we require 2 multiplexes of 2:1 mux, and again it is divisible. So again we have to divide. So at third stage, how many mux are required? 2 divided by 2, that is 1. Now we have to add at every stage. What we get at first stage, how many 2:1 multiplexers are required? That is 4. Then at second stage, how many multiplexers are required? 2. And at third stage, we require 1 multiplexer. So it is total 7. Okay. So total 7 2:1 multiplexers are required to implement 8:1 multiplexers. Okay. So option B is the correct answer for this question. That is option B. So I hope you understand this question. So can we move to the next question? It is 7. Okay. Moving to the next question. Next question is identify the output of the following circuits. So here 4:1 multiplexer is given and we need to find out the output, that is F. Okay. So already we know that what is a truth table or what is a truth table of 4:1 multiplexer and how we can write the output. So these are the, as we know that these are the input signals and these are the selection lines and this one is the output, right? From here we can select from PQ, P different these input lines. Okay, that it is P key Y. So how we can select? If P and Q are 0 0, how many combinations are will we need? 4, right? 0 1, 1 0 and 1 1. If P and Q both are 0, then we will select I0. Then I0 will pass to the this output to this one. And when P and Q are 0 1, then I1, and when it is 1 0, here I2, and where both are 1, then I3, right? Then how we can write the overall output? Sum of all those. So here we can write directly P dash Q dash I0 plus P dash Q I1 plus P Q dash I2 plus P Q I3, right? This is a truth table of 4:1 mux, and it is now we need to say what are the values here it is coming, and then put these I0, I1, I2, I3 values to in this equation in order to find out what will be the final output F. This F. Okay. I can write it correctly. It is F. So let's see. Here it is 0, it is ground, so that means 0, right? Now it is a NOT gate, so the output this will be inverted, so 0 1, here again 0, right? Here at I1 what are coming? 1, in I2 also 1, and at I3 the input is coming 0 because it is directly connected to the ground. Okay, so now we need to put these values to I0, I1, I2 and I3 here. So I am writing it here. F is equal to P dash Q dash into 0. What is the value of I0? I0 is 0, right? Plus P dash Q I1 is 1 plus P Q dash is I2 is also 1. So we are writing here 1. Then P Q I3 is 0. So 0. So these will be cancelled out. That means 0. So what left? If P dash Q is multiplied by 1, so P dash Q only. Similarly, here also P Q dash. Right? It is in which form? XOR form, P dash Q plus P Q dash. So we can write it P XOR Q, right? So what? So this one is a final output F. So which option is correct? Option A. Okay, option A is the correct answer. Okay, I hope you have understand. So can we move to the next question? Yeah, okay. Thank you. Okay, so moving to the next question. The next question is, without any additional circuitry, an 8:1 mux can be used to obtain. Option A is some but not all Boolean function of three variables. Option B, all functions of three variables but none of four variables. Option C is all functions of three variables and some but not all of four variables. And option D is all functions of four variables. So here 8:1 mux is given and there is nothing, no additional circuitry is given. So how many Boolean functions we can implement? So we can write it 2 to the power n form, right? In order to find out the selection line, or that can be written 2 to the power 3:1, right? So three variables we can make for it, sure, because here 8:1 marks one output. Three selection line will be there because n is equal to 3. So you can write it x, y, z, and here 8 input lines will be there. 4, 4, 8. So three variables for sure we can make it, but without any additional circuitry, if we can give one input, any one of, or so some but not all four variables we can make. So already we know that a mux is a combinational circuit that accepts data from the multiple input lines and pass it to the single output line. Okay, through selection signals. So for n:1 mux, n is the number of input. Here 8 is the number of input and n small n is the number of selection line. So a multiplexer with n data select inputs can implement any function of n variable, that means 3 variable, and some function of n plus 1 variable. So by n plus 1 means 3 plus 1, sum of 4 variables. Okay, so all function of 3 variables and some but not all of 4 variables. Okay, option C is the correct answer for this question. Okay. Okay, so moving to the next question. The next question is, identify the output of the following circuit. So here again 8:1 multiplexers is given and here selection lines are given here. Okay, not from here, it is given this side, and these are the input. These are the inputs and this is the selection line. So okay, so in order to find out the f, first we need to write the what will be the truth table of this one. So from here as to this line, so we can write it a, b, c and output y. Then we will make the final output f. Then number of combinations we can make 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 triple 1. Okay. Now output. What will be the output? So let's first see to what the inputs are going. Here, here the 0, 1, 2, 3, that means I0, I1, we can write it like this only for our convenience. Okay. So for here we can, it is directly coming D, that means D, and same for 1 also, again D, and for 2 it is D dash, right? And again for 3 and 4 both are 0, the inputs are 0, so we have to write 0, and for 5 it is D again, and for 6 and 7 it is 1, the input are 1. Okay, so we have made a truth table. Now we have to write the overall output, that is F. Okay, so how we can write it? F, it is 0, two inputs are 0. So first A dash, B dash, C dash into D, right? For example, we have write A dash, B dash, C dash, I0. So I at the place of I0, I am directly writing the D. Okay, the value of I0. Then plus A dash, B dash, C, D. Again plus A dash, B, C dash, D dash, right? And now it is 0, so all functions will be 0, so I am not writing it because already it will be 0. So here again, here the output is D, input is D, so we can write it like A, B dash, C, D plus A, B, C dash, right, and multiplied by 1, so that 1 will be disappear, so that will be same A, B, C. Okay, so this will be the overall output. Now here it is given in the form of min terms, right? So now we have to make a K map in order to find it out. Okay, we cannot directly write it from here because here D is given here. It is also input and ABC is also a input or variable. So we need to minimize it. Okay, so now we have to make a K map in order to find out and put all these things into K map so that we can find out the overall min terms. So where I can make it here. Here let's see AB this side and CD this side. Okay, so it is 0 0 0 1 1 1 and 1 0. It is also 0 0 0, 1, 1, 1, 1, 0. So first term is A dash, B dash, C dash and D. So A dash, B dash is this row, right? And C dash D. C dash D will be this one. So here we have to put 1. Again the next one is A dash, B dash, C, D. So A dash, B dash is this line and C, D only. So this one, C, D. Now next one is A dash B. So A dash B will be second row, right? A dash B, C dash, D dash, C dash, D dash, that means first column. So this one is A dash B, A dash B, C dash, D dash, right? This three terms has been done. Now next term is A, B dash. A, B dash means fourth row and CD. That means CD will be third column, right? Now next one is A, B, C dash. So AB will be the third row, right? AB only is there. So AB and C dash. C dash from where we can find out? If we take common in these both two, so C will be this side, so C dash from we will get here from here. So we have to put here. So from if we make a pair from here, we will get AB C dash, right? Now next is ABC. So AB is the same one, and again we need to find out the C only. It is C dash. So if we take one in both common in these two columns, we will get the C only, right? So this one. Now we need to check at which places at there is a 1 will be there because we need to find out the main terms. Okay. So A, B, C, D will be summation of. So first it is 0. Already we know 0, 1, 2, 3, right? It is a K map. So 0, this one, this first cell is 0, 0, 0. Then next one 1, 2, 3. Then 4, 5, 6, 7. This one is 8, 9, then 11, then 12, 13, 14, 15. Already you know that. Already you have studied the K map. So this one is 0. So 0, 1 and 2, 3. So 1 and second one at 3 places. So 3. Now next one is at 4th, right? 4. Now this one is 4. So 5, 6, 7, 8, 9, 10, 11. Then it is at 11. Now next one is 12, 13, 14, 14, 15. So we have to write 12, 13, 14, 15. Okay. So what we have got f is equal f in brackets of a b c d equal to min terms 1, 3, 4, 11, 12, 13, 14, 15. Now we have to match in these options. So option B 1, 3, 4, 11, 12, 13, 14 and 15. So option B is the correct answer for this question. Okay. So I hope you have understand these questions. Can we move to the next question? Okay, so moving to the next one. Yeah, hello. Just a minute, my system got hang. So yeah, just so yeah, I'm audible. Yeah, okay. The next question is find the function implemented by the following circuit. Which function we can implement by the following circuit. So here it is given 3 to 8 decoder. That means 3 input lines and 8 output lines. Okay. So what will be the truth table for the decoder? Already we know that here input we are giving in the different combination and corresponding that output will be 1. Okay. So in the normal decoder circuit, it is written as D0, D1, D2, D3, D4, D5, D6, D7 or individual. We will calculate the output, right? So let's first find out the what will be the truth table for this. Then we will make the function. Okay. So inputs are already we know that is x, y, and z. And what are the outputs? That is 0, 1, 2, 3. So I am writing in terms of D0, D1, D2, D3, D4, D5, D6, and D7. Okay, this is D. So what will be the different combination? That is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, next one 1, 0, and last one triple 1, right? Now for 0, 0 only the output D0 will be activated, that will be the high, and all other are 0, right? Similarly for 1 we are giving here that this it is 0, 1 already we know that this correspond to 2 value and this correspond to 3, 4. When we are giving 1, that is then D1 will be 1 and all other will be 0. Similarly for D2 this one, and we will do like this in the last one. D7 will be high and all other will be 0. And how we can write it the output? So for D0 example, we have to write it this way. X dash, Y dash, Z dash. For D1, X dash, Y dash, Z. For D2, X dash, Y, Z dash. For D3, X dash, Y, Z. And for D4, this is X, Y dash, Z dash. For D5, this will be the X. For D4, that will be the X, Y dash, Z dash, X, Y dash, Z. D6 will be X, Y, Z dash, and for D7, X, Y, Z. Okay, now add sum. It is XORing, sorry, it is OR of 1, then 2, 4, and 7, right? So I am writing like D1 plus D2 plus D4 plus D7. Add C output, what the outputs it is adding, that is D3, then D5, then D6 and plus D7, right? So from here we can get the directly whether, because it is clearly written what the following circuit it is implemented. So it is given half adder, full subtractor, full adder and multiplier. Okay. So from here also we can say that this, here we can S is equal to sum bit of the full adder, right? And carry is, it is the min terms of the carry of a full adder. So already we know that what would be the min terms for full adder for sum, that is, if you remember, 1 2 4 7, right? And for carry the min terms are 3 5 6 7. If you compare, it is adding the two different functions, that is S and C, and the output is for S 1 2 4 7 and for C it is 3 5 6 7. Okay. So if you add it in these terms and you will find out, then you will get X XOR Y XOR Z. If you add these D0, sorry, D1, D2, D4, D7, from here you will get X XOR Y XOR Z. You can solve it. And then this, you can say that it is some equation of full adder, and for carry you again you have to add from here and you will get the XY plus ZX XOR Y from here. Then it is a equation for carry. So from here you can say that it is a full adder, it is implementing the full adder. Otherwise you can directly see from here, and let, if you know that what will be the min terms for full adder and full subtractor, if you remember, then you can directly take it from here. Okay, so option C is the correct answer for this one. Okay, so I hope you understand this. Okay, so can we move to the next question? If you have any doubt, you can ask. Otherwise, we can move to the next question. Okay, so moving to the next question. So next question is, if A is equal to A1, A0 and B is equal to B1, B0 are 2-bit input binary numbers, output C is equal to C3, C2, C1, C0 implements. Now what it implements, this circuit, what it is implementing. So from here we can see that A is equal to A1, A0 and B is equal to B1 and B0. It is given with different input. Okay. So first we need to find out the C naught. So what is the C naught? C naught is A0 and B0, right? It is an AND gate. So A0 and B0. From here we can get the C naught. Now next one is C1. C1 from the half adder we can get, first one is A0 P1, A0 P1. Already we know that half adder adds two bit numbers A0 B1, and next input is A1 B0, so plus A1 B0, and the carry of the first half adder move to the next half adder. So what will be the output of C2? From C2, one is the carry plus, we can, let's see, X plus, it is A1 B1, A1 and B1. C3 is not given anything, so we can take it like Y. Okay, now we can see the options. From the options, it is a 2-bit by 2-bit division, whether a 2-bit by 2-bit multiplier, a 2-bit adder, or a 2-bit subtractor. So from the outputs, we cannot say that it is a 2-bit adder, right? Because already adder equation sum and carry, and for subtractor borrow and we know. So these two will be cancelled in these two. So let's first check for multiplier, a 2-bit by 2-bit multiplier, because here 2-bit by 2-bit is also given, and it can be a 2-bit by 2-bit division. So first we will check to the multiplier, because it is on, if you see from the video lectures, so from directly you can say that it is a 2-bit by 2-bit multiplier. Okay, so let's see a1, a0, b1, b0. Just check whether it is coming or not. So first we will multiply here. So what we will get? A0, B0 from here, A1, B0. Now next one, B1, sorry, A0, B1. Now next one is A1. Here I don't have a space, but I am writing on this side, A1, B1, right? Now we have to add this. So A0, B0, and here, and here there is a 0 only. So A0, B0 is directly, we can write here, we need to add A1, B0 plus A0, B1, right? Now if there are some carries, so move to the, let's see, it is generating one carry, so it is X. So now next one is X plus A1, B1. Now if it is generating some other carry, so it is Y. So if we name it, it can be a C0, it is C1, it is C2, and this one is C3, right? So if we compare this, so it is a matching with the multiplier output. So we can from here say that 2-bit by 2-bit, it is a 2-bit by 2-bit multiplier circuit. Okay. So option B is the correct answer. Okay. So I hope you understand this. So moving to the next question. So next question is, a 4-variable logic circuit can be designed using, a 4-variable logic circuit can be designed using a 16:1 multiplexer, an 8:1 mux and 1 inverter, and option C is a 2 8:1 multiplexer and 1 2:1 multiplexer, and D is any of the above. So anyone of you can answer this question, at least try to answer. Just give it a try to solve this question. Just think about it. Yeah, 4-variable logic circuit can be designed using 16:1 multiplexer. 16:1 multiplexer means 16 inputs, and it is 16. So it can be added 2 to the power 4. That means 4 selection lines and 1 output, right? 16 into 1 multiplexer. It is 16 2 to the power 4. 16 can be written 2 to the power 4, where n is equal to 4, means we can make a 4-variable logic circuit. We can take a 4 variables in order to implement. Now option A is correct. We can design 4-variable logic circuit into 4 into 16 into 1 multiplexer. Now next one is 8 into 1 multiplexer per and 1 inverter, right? So for 8 into 1 multiplexer, there are 8 input lines and 3 selections lines, because 8 is 2 to the power 3, means n is equal to 3, means 3 variables if we apply one inverter, already we have seen the previous, let's input D, we can, and by using one inverter we can get any other, we can take any other variable and we can make. So from an 8 into 1 mux and one inverter we can make, okay, 4 variable logic circuit. That one is also correct. Next one is 2 8 into 1 multiplexer and 1 2 into 1 multiplexer. From here it is also possible because already we are making here 2 8 into 1 multiplexer. For one multiplexer we can take 3 variables, and for next multiplexer we can also take 3 variable, 1 variable to any other variable, and 1 mux is also there. Here we can also give 1 in variable. So from here it is also possible to make a 4 variable logic circuit. Okay, so option D is any of above. So any of above in these three options we can make a 4 variable logic circuit. Okay, so option D is the correct answer. Okay, so I hope you understand this. So moving to the next question. The next question is, how many 2 into 4 decoders are needed to design a 4 into 16 decoder, right? So we need to find out how many 2 into 4 decoders are required to make a 4 into 16 decoder. So again, we already seen that how we can do. Just we have to divide the 16 by 4 at different stages. So let's see, at first stage, uh, yes, Harsha, what do you want to say that? What you have shared? Okay, you want to ask something? Okay, so let's, at first stage, let's see how many 2 into 4 decoder are required. So that is 4, 2 into 4 decoder required. Let's see, and in the next stage, how many decoders are required? 2 into 4, 4 divided by 4. So that will be 1. So total number of decoders required to design a 4 into 16 decoder is 4 plus 1, that is 5. 5, 2 into 4 decoders are required to design 4 into 16 decoder. Okay. So option B is the correct answer for this question. So total 5 2 into 4 decoders are required to design a 4 into 16 decoder. Okay. Okay. So yeah, moving to the next question. The next question is, add the two VCD numbers, that is the VCD numbers are 1 0 0 1. BCD stands for binary coded decimal. Okay. Next one is 0 1 0 0. So already you have studied that BCD number is only for 0 to 9, and for 9 to 15 it is not a valid number. Okay, it is valid till 0 to 9. Okay, so 0 to 9 we can say that it is a valid VCD number, and if it's 9 to 15 or any other number, this is an invalid VCD number. Okay, so if we add, so 9 is also a valid VCD number, BCD number and it is 4. So it is also a valid BCD number, right? So if we add this, so decimal equivalent of this is 9 and decimal equivalent this is 4. So if we add it 1, 0, 1, 1. So if we add two decimal number, we are getting 9, 4, 13. Okay, it is a decimal number. And if we convert it, it is also 8, 4, 12, 1. It is also coming 13. But 13 is not a valid BCD number, right? So what we are doing, so make it a valid BCD number, we have to add 6 into this 13. 0, 1, 1, 0. It is a procedure. So 1, 1, 1, 1, 10, 0, again 0, 1. If we discard it, you will get a valid BCD number, that is 3, right? So, but we can't remove this. So, if we put 0, 0, 0 in order to make it valid BCD number, so we will get 0, 0, 0, 1, 0, right? It is matching with this. So, option C is the correct answer for this question. Okay, so 0, 0, 0, 1, 1, 0, 0, 1, 1, right? It is 0. Okay, have you understand this? Okay, I hope all of you are getting. So moving to the next question. So yeah, next question is a 3-digit decimal numbers require for representation of the conventional BCD format. Okay, let's take any 3-digit. Let's see, 2, 6, 8. Is it 3-digit? A 3-digit decimal number requires for representation of conventional BCD format. So already we know that to represent a 1 decimal digit, how many bits are required? 4 bits. For example, for 2, what is the representation? 0, 0, 1, 0. Yeah, for 1 digit, right? Now for 3 digit, how many bits are required then? And what is it? The BCD representation for 6? That is 0, 1, 1, 0. And similarly for 8, 1, 0, 0. Right? So total how many bits are there? We can take any 3 digits. You will get the same. For every digit corresponds to a 4 bit, right? So 4, 4, 4, 12. 12 bits are required for representing a conventional BCD format. Okay, so option D is the correct answer. Okay. Okay. So yeah, I hope you understand this. So moving to the next question. Okay. So yeah, next question is delay for 128-bit carry look ahead adder. So here, for what will be the delay for 128-bit carry look ahead adder? So already we know that what is the formula. It is also given in the lecture slides. So it is T look ahead carry adder. I am writing look ahead. So T corresponds delay. So for look ahead adder, what is the formula? That is 4 log 4k, right? Delay for k bit carry look ahead error. Here k is given is 128, right? So 4 log 4 128. So how we can write? If we want to write it to the 4 to the power 4, because if 4 will be 1 only. So 128 we can write it 4 into 4 is 16, into 4 is 64, into 4, right? So it will give 64, or it will give the 256. If 4 to the power 4 we will get 256. If 4 to the power 3 then we will get 64 only, right? But it is a 128 bit, right? So we can't take 4 to the power 3. So if we take 4 to the 3.5 approximately, or 3.2, so we can take it approximate. So you will get 4 log 4. We can take the greater one always. Okay, 4. So you will get 4 into 4, that is 16, right? So it is 16, because we can't take 4 to the power 3, because it is getting only 64. We can take the upper one, 64, because it is greater than the 64. Because you will get 4 to the power 3.5 approximately, you will get 128. So we can approximate it, approximately 4. Okay. So you will get the approximately of that. So 64 is the correct answer. The formula is given in the slide. Okay, I hope you understand this. So moving to the next question. Can we move to the next question? Have you understand this question? Okay. Okay, thank you, Harsha. Okay. Okay, so now next question is, a 2 to 1 multiplexer can realize which of the following? Only and or not, only or, only not, or option D and or not. So anyone of you can answer this question? 2 into 1 multiplexer, already we know that. Two inputs are there, one output will be there. We can write it I0, I1, and there will be the one selection line only. So S, right? 2 to the power 1. So n is equal to 1. So there will be the one selection line will be there, right? Let's S can be 0, when only two combinations are possible. So what will be the output? When it is 0, then the selection line will select the I0, and if it is 1, then it will be the I1. So overall output will be, let's put it y, S dash I0 plus Si1, right? So if we implement it, how many gates are required? So from here we can see that 2 AND gates are required, right, to multiply this, and to add these two, one OR gate required, and it is yes dash, so one NOT gate required, right? So first take one AND gate and another AND gate, and we have to OR these two input. It is y.
Lara,
Yeah. So it is I0. Let's see. Here we have given S. It is I1. And if we take the inverse, here we will get the S dash. So I0. So it is I1. It is I0. Right? Now it is correct. I0. Here it is I1. Right? So S into I1. Here s dash into I0. If we add this, you will get the overall function this y s dash I0 plus s I1. So total AND gate, two AND gates, one NOT gate and one OR gate. So realize which of the by AND gate, OR gate and NOT gate. Okay, is the correct answer. If we want to design or realize 2 into 1 multiplexer, so AND gate, OR gate and NOT gate are required. Okay. Okay. So I hope you understand this. Okay, I hope you understand this. So moving to the next question. So next question is a delay for 128 with triple carry adder is. What will be the delay for 128 with? It is for triple carry adder. Okay. So from it can be calculated if you have gone through the video lectures. So it is the direct formula. So the delay it is a delay. The delay for n bit. It is a triple carrier. Okay, it is for triple carrier. Previous one is look ahead carrier. Okay, the delay for n bit triple carry header is 2n. Okay, it is a formula for triple carry adder. So here n is given 128. So let's see, it is I am representing for T R triple carry adder, triple carry. So 2 into 128, you will get 256. Okay, so delay for 128 bit triple carry adder is 256. Okay, option D is the correct answer. Formula is 2n. So the delay for n bit triple carry adder is 2n. Okay, so the delay is 256. I hope you got. So moving to the next question. So next question is the X3 code equivalent to the BCD code is. What is the X3 equivalent code for BCD 3 code? So BCD code 3 code is given 0110. It is a BCD code. So already you know that if we add 3 into a BCD code, we will get the XS3 code. 3 code. Okay. So BCD code plus 3. So 0, 1, 1, 0, 0, 0, 1, 1. You will get 1, 1, 0, again 1, 0, 1. What we will get? It is equivalent to 9, right? It is 6, it is 3. So which option is correct? Option A is the correct answer. Yeah, that's 9. Okay, it is 9. Option A is the correct answer. We have to add 3 into a BCD code in order to get the XS3 code. Okay. Okay. So moving to the next question. The following logic diagram possibly shows the structure of option A is binary to decimal converter. Option B,
Ma'am,
yeah.
if we get XS3 code greater than 9, do we, it will be valid only, na?
No, that one is not a valid
Then
because
we have
BCD
to add
code is
6 to it again.
hmm, yeah,
In this example, we got 9. Is it 1001?
yeah. Just
But
I'm
there may be a case where I'll get 1100, suppose.
if
So
you
in
have
that
gone through
case,
the video lectures, so you have seen that BCD code is written for 0 to 9 and okay, and
yeah.
XS3 code is also 0 to 9, it is valid.
Okay,
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 we can get in the 9 we can add 3, that we will get, but after 9 of BCD code it is X X X only, means that
okay.
one is invalid. Okay. Okay, so moving to the next question. So the following logic diagram possibly shows the structure of this diagram is to which structure? This is a binary to decimal converter. Option B is binary to gray code converter. Option C is gray code to binary code converter, and option D is none of above. So this structure it is XOR gate, right? These are the XOR gates. So already we know that this is not a binary to decimal conversion. This option is incorrect. Now we have to check whether it is a binary to gray code conversion or gray to binary conversion. Okay, so in the binary to gray to gray, already we know that we are XORing to between the inputs in order to convert the binary to gray conversion. So we have to give the inputs. Let's see, first one will be the same only. Now next one, the output, and for next one we have to take this one and next input. Okay, so let's see x0, x1, x2 for next. So it is not a binary to gray conversion because here we are taking from output to the input. First it's same, let's see x0. For next bit we are XORing to the input to the next output. So it is possible only gray to binary conversion. Okay, let's see 1 0 1 1. So for gray to binary conversion we take first bit as it is, then XOR the output of the first bit to the input of the next bit. So 1 0 1, right? Now next XOR these two, 1 1 is same, so 0 again, 0 1 1. So it is a gray to binary conversion. Okay, so it is a gray code to binary code conversion. Okay, so I hope you understand this. So it is a gray code to binary conversion. Because binary to gray we are XORing the inputs, and in the gray code to binary it is XORing the input and output of the first bit. Okay, so it is a gray code to binary code conversion. This is the structure of binary gray to binary code conversion. Option C is the correct answer. Okay, so yeah, I hope you have got this. So moving to the next question. A 2-bit binary multiplier can be implemented using two AND gates. Option A. Option 2 is 2 XOR gate and 6 AND gates in total. And option 3 is 2 input NOR and 1 XNOR gate. And option 4 XOR gate and shift registers. So till now we have didn't study the shift registers. So it can be made, but now it is not in the option. Shift register we can't make a 2-bit binary multiplier, so this option is cancelled. So now first we will check what will be the outputs of the 2-bit binary multiplier. So this is a, let's see, it is a 2-bit multiplier. Here it is the input A, it is B, it is a 2 bit, it is also 2 bit, it is also 2 bit, it is a output. Let's say F. So A means A1, A0, A1, A0, B means B1, B0. Let's multiply and see that A1, A0, B1, B0. So here we will get A0, B0. Now in the next multiplication A1, B0. This one is A1 and this one is B0. Now next it is 0. So now here A0, B1. Now next one is A1, B1. Right? Now here if you add A0, B0 and it is A1, B0 plus A0, B1 and A1, B1. Right? Let I'm giving some names. Let's just a P0, it is a P1, it is P2 and last carry is P3. Okay, so let's say P0 is A0 V0, right? P1 is A1 V0 plus V1 A0, right? P2 is A1 V1 plus some carry, let's say X, and P3 is then another carry which generated from here. It can be, it can not be. Okay, so let's first check how many AND gates are required if we want to multiply. So 1, 2, 3, 4, right? 4 AND gates here, and to implement 2-bit binary multiplier already we have seen that 2 half adders are required, right? And for 1 half adder we know that 1 XOR gate half adder, for 1 half adder we require 2 XOR gate and 1 AND gate, right? So for 2 half adder we required, so for that 2 XOR gate, that is 1 XOR gate and 1 AND gate, 2 XOR gate and 2 AND gates and other 4 AND gates. So total 2 XOR gates and 6 AND gates in total are required to implement a 6-bit binary, 2-bit binary multiplier. Okay, here 1 XOR gate and 1 AND gate, and for 2 half adder 2 XOR gates, 2 half adder, I'm writing it here because otherwise 2 XOR gates and 2 AND gate, and for these two total 4, so total we will get 6 AND gates and 2 XOR gates, right, to implement a 6-bit binary multiplier. Okay, so I hope you understand this. So moving to the next question. Now next question is, a single bit comparator compares two numbers A and B and produces three outputs. That is y1 if A is equal to B, y2 if A is greater than B, and y3 if A is less than B, as given below. Okay, so these are the options which are given. Then choose the correct answer from the options given below. So what will be the first? Let's see what will be the comparator circuit. Here it is already given only two numbers A and B. So that means we have to compare two bits. That it is A and it is B. And there are three outputs. Let's first one is A is equal to B, right? It is said as y1. Next one is set to y2. Okay, I'm writing it here so that A, B, two inputs and three outputs. Okay, first one is y1, that is A is equal to B. Next one is y2, that is A is greater than B. Next one is y3, that is A less than B. A less than B. So number of possible combinations, that is 0, 0, 0, 1, 1, 0 and 1, 1. Okay, here it is 0, 0, that means A is equal to B, right? A and B equal. Then we have to put 1 here and all other places 0, right? Because y1 is correct. That means A is equal to B. Now next one is A is 0 and B is 1. What does that means? A is less than B, right? So means this will be correct. A is less than B. Here A is 0 and B is 1. So that means A is less than 0. Now next one is A is 1 and B is 0. So which one is correct? Which will be 1? That means this A is greater than 1 will be 1. Now is also 1, B is also 1. So again y1 will be 1 and all other places will be 0. Right? Now here let's we are writing case 1 if A is equal to V. So let's calculate what will be the function. So that is y1. So from here we can take it. First one is when it is 1, when A and B are 0. That means A dash, B dash. And when other places it is 1, where A and B both are 1. That means A, B. Right? So already we know that it is XNOR, expression of XNOR. So we can write it like this also. A XNOR B. This is the expression for XNOR gate. Right? Already you know that. The next case is case 2. If A is greater than B. Right? So what will be the output? That's y2. Already it is given y2 if A is greater than B. So at which it is given at 1 A B dash. From here we can write it. What is the corresponding input? That is this one. So A B dash. Now third case is, I am writing it here. Case 3. If A less than B, then what will be the output? That is y3. Y3 is 1 at this place, second row. So that means A dash B. Right? Now we have got a y1, y2 and y3. y1 we have got A XNOR B and y2 we have got A B dash and y3 A dash B. So let's check which option will be correct. First one A is y1 A XNOR B, y2 is A B dash and y3 is A dash B. So this means that is correct. Option E is correct. Next one is wrong because this one is A XOR V, so we didn't get A XOR V. Now next one is also y1 is A plus B, but we have got A XOR, so this one is also not correct. Now option D we can check. It is written in this format. So a dash b dash plus ab. So y1 is correct. Now check y2. AB dash, this one is also correct, and this one is, so option D is also correct. Okay, so when option in this, choose the correct answer from the option. So A and D are correct. So option 4 is the correct answer. A and D only the correct option. Okay. Okay, so I hope you have got this. How to solve this the comparator related to questions. Okay, so moving to the next question. So the next question is 2-bit numbers A1, A0 and B1, B0 are given as a inputs to a 2-bit comparator. The comparator output, that is P, Q and R, if A is less than B, A is greater than B and A is equal to B. Then for the circuit shown below, the probability that S2 is 1, that will be the one. What will be the probability that S2 will be 1? Okay, now we need to check when S2 will be 1. So for S2 becoming 1, the inputs of the decoder must be 0, 1, 0, right? It is a 3 into, so already we have seen the previous 0, 0, 0, 0, 1, 0 and 0, 1, 1 like this. So the combination, if 0, 1, 0 will be there in the inputs, then S2 will be the 1 only, right? So what will be the combination? Means P, Q, R, P, 0, 1, 0, right? Q must be 1. That means Q must be 1. What will be the condition? A greater than B, right? That is A greater than B. So for getting A greater than B, then it will be the one. What will be the possible combinations from there? If when A always will be the greater than B. Okay. So first thing, you can make a truth table. From there you can find it out at which places A will be greater than. So for here 4 inputs are there. So you will get 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. Here you can write it A1, A0, B1, B0. So you have take all the possible combinations, right? So now we have to check A must be greater than B. Okay, so we can directly check it from here. Other way, you can make a that truth table and check it from there. So I am taking the options. So I think you have understand. You will understand. Not sure if you not understand, then I will go through all the process. Then so let's when A will be greater than 0. So what will be the cases? So first case is when P is 0, 0, okay, and A is 0, 1, 1, 0 or 1, 1. A means A1, A0, okay. So first case is when B will be 0, 0 and A will be greater. Here A is greater, right? 0, 1, 1, 0, 1, 1. All three combinations are greater than B 0, 0, right? So first, these are the combination where A is greater than B. Now next case is when P is equal to 0, 1. Then what are the possible combination where A will be greater than 0, 1? That is 1, 0. and 1 1, right? No other possible combinations, right? So here two possible combinations are there where A is greater than B. Here total three possible combinations are there where A is greater than B. Now next case is when B is 1 0, right? Then at which case the A, yeah, that is 6 by 16. Okay, you are going very forward. So if A is 1 1, in that case A will be greater than B. So, okay, so here total three combinations are there. Here total two combinations are there. Here one. So total combination where total combinations where A is greater than B is 6, right? So total combination we have got 6. 3 here, 2 here and 1 is from here. Okay, where A is greater than B. The total combinations where A is greater than B is 6. Now, in order to find out the probability, we have to find out the total comparison that will be occurred. Okay, so here 4 bits are there. So 2 to the power 4 means 16 combination and 16 comparison we have to make. So total number of comparison is 16, right? So I'm writing it here, total comparison is 16 and total combinations where A is greater than B is 6. So in order to find out the probability where S2 is equal to 1 will be number of comparisons where A is greater than B. Maybe I don't have a space, so I can in it from here. Then I can write. So I'm writing here P probability of S2 is equal to 1 will be number of comparisons. I'm writing it short. A is greater than B and total number of comparisons. Total number of comparison. For comparison, I'm writing only COMP. So number of comparisons where A is greater than B is 6, right? And total number of comparisons is 16. If you divide it, you will get 0.375. Okay. So answer is for this is 0.375. So the probability that S2 is equal to 1 is 0.375. I can write here clearly 0.375. Okay. Okay. So I hope you got this question. So moving to the next question. Yeah. So next question is the output Y of a 2-bit comparator is logic 1 whenever the 2-bit input A is greater than 2-bit input B. Okay. And 2-bit input A is greater than 2-bit input B, then output Y of a 2-bit comparator is logic 1. The number of combinations for which the output is logic 1. So we have to find out the total number of combinations where A is greater than B. So already in the previous case we have solved this. So we need to find out total number of comparisons where A is greater than B. So let's check by, so the possible combinations are the possible combinations when A is greater than B. First case is if A is equal to 0, 1 and B is 0, 0. This is the first possible combination where A is greater than B, right? Now next case is we can't take A is equal to 0, 0 because 0, 0 is lowest. So we can't take 0, 0. So we are taking the larger. When A is equal to 1, 0, then what will be the possible combinations where B will be less than that, that is 0, 0, and second one is 0, 1, right? Then in that case, A will be greater than B. Now third possible combination is when A is equal to 1, 1, right? And B can be 0, 0, 0, 1 and 1, 0. In three cases, A will be greater than B. In all these cases, the A is greater than B, right? So let's calculate the possible. So 1, 2, 3, 4, 5, 6. So total 6 number of combinations are where output is logic 1 when A is greater than B. Total number of combination is 6. From here you can add. Okay, 3 plus 3, 6. 6 for 6 combination A is greater than B. So option 2 is the correct answer for this question. Okay, now you can solve it from here. Otherwise, there are one formula is also there. So 2 to the power 2n minus 2 to the power n divided by 2 from here. So here n is equal to 2 bit already is given output of a 2-bit comparator n is equal to 2. So if we put 2, so 2 into 2 will be 4 only and 2 to the power 2 divided by 2. Let's check. So 2 to the 4 will be 16 minus 2 to the 2 is 4 divided by 2, right? So here we will get 12 by 2. So here also we are getting total 6 combinations where A is greater than B. You can take it from any combination. Okay. For this type of question only. Or
Hello, ma'am.
yes.
Is this formula applicable for all the uh, condition like A is greater than B and A is less than B?
Yeah, you can check it for A less than B. And now you can you tell me, we can calculate it from here also. A is less than B. For what are the possible combinations where A is less than B? Where 0, 0 is there. So 0, 0 for 0, if it is a 0, 0, then possible combination will be 0, 1, 1, 0 and 1, 1 in that case. And when it is 0, 1, then possible combination is 1, 0, 1, 1. Again it is 6. Yeah, it will come 6. Okay. Have you got this?
Yes, ma'am. Thank you, ma'am.
Okay. So moving to the next question. Next question is the gray code for A5. It is in hexadecimal is equivalent to. So it is given the hexadecimal. So first we need to convert it into a binary. So what will be the binary equivalent of A5? A is 10, right? So for A is 1010 and for 5 it is 0101. It is a binary equivalent of A5. Okay. Now we need to find out the gray code. It is a binary. Now we have to perform the binary to gray code conversion. Okay. So 10100101. So for binary to gray code conversion, we know that first bit will be the same, and now we have to absorb the next bit, first bit to the next bit. So 101 will be there, right? For this one again we have to absorb these two, absorb, and output is 1 again. Now we have to absorb these two, then you will find that as following 101 Now again we have to exhaust these two, so 0 0 will be 0, and again exhaust these two, we will get 1. Again if we exhaust these two, we will get 1, and again if we exhaust these two, we will get 1, right? So output is binary to gray conversion 1 1 1 1 0 triple 1. Now we need to check. So option 1 is the correct. 4 times 1 then 0 triple 1. Okay. So it is a binary to gray code conversion. We have to take first bit as it is now, then XOR to the next bit and get output. Again XOR to the first one, then next one, and then output will be written. Okay. So I hope you have get this binary to gray. Binary to gray code conversion. Okay, moving to the next question. So how many 3 into 8 decoders are required to construct a 4 into 16 decoder? So anyone of you can answer this question, because already we are, I think this one is a third question based on that. So it is given we have to construct 4 into 16 decoder by using 3 into 8 decoder. So what we need to do, we have to take first what we want to construct and divide it to the for which we want to construct. So 16 by 8, let's it at first stage how many 3 into 8 decoder are required at first stage, how many? So it is 2, right? Now again that 2 divided by 8 at the second stage, so it can't be divided, so it is 0 at second stage. It is 0. If we add these two, we will get 2. So only 2 decoders are required to construct a 4 into 16 decoder. That means 3 into 8 decoders are required to construct a 4 into 16 decoder. So first option is correct. Only 2 decoders are required. Yeah. Okay. So moving to the next question. So next question is, a 3 into 8 decoder is shown in the figure. Find out the output. F x2, x1, x0 in the form of x2, x1. So how we can get it? It is a 3 into 8 decoder, 3 input and 8 outputs, and F is equivalent to D. If what is symbol of XNOR gate, right? So D1 plus D4 plus D7 dash, right? It is the output D1 D1 plus D4 plus D7 dash. Okay. So what are the possible combination? Already we know that from the truth table of the decoder. So it is a x0, it is in capital, so write it in the capital. X0, x1 and x2, right? And we can write it directly, otherwise we have to write the very large truth table, that is from at which places the output. Already we know that at 0 0 0 D0 will be high and all others are low. Already we know that. I'm not writing it. I'm directly writing the F. Okay. So at which places the F will be high and at which places the F will not be high. Okay. So 0, 0, 0, 0, 0, 1, 0, 0. So this is 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? Now we have to check at 0, 0, 0, D0 will be high, right? Then F D0 will be D0 will be 1 and all other are 0, right? So if we 0, 0, 0, ignore that things D1, D4, D8, these are the 0, then we will get 1, right? Because at 0, 0 it is 1 and all other combinations are 0. So 0, 0, 0. So 0, 0 will be 0, 0 dash, right? 0 dash will be 1. So that's why I am writing here 1. Now see to the next combination. So I am removing it here. Then let you know. So for next combination 0, 0, 1, that means this D1 will be 1 and all other bits are 0, right? From the truth table. So 1, 0, 0. So you will get 1. So 1 dash. F will be 1 dash. So 1 dash will be 0, right? Here at this position we will get 0. Now check on the next. So for next, can anyone of you tell me what will be the possible combination, what we will get the output? Any one of you want to tell?
It will be 1.
0, 1, 0 for 0, 1, 0. D2 will be 1 and all other 0. Then again we will get 1, right? And for 3, D3 will be 1 and all other possible combinations are D0, D1, D2 are 0. So here we are adding D1, D4, D5. These are 0. So 0 will be F dash, the output dash 1. Again for 1, 0, 0, the D4 will be 1, right? And all other possible combinations are 0, 0. So D1, D4 will 1, 0, 0. If you added 1 and it will be again give you 0, right? Here it is 0. If you check the other possible combinations, so you will get this one for F, it is 1. So you will get 1, 0, 1, 1, 0, 1, 1, 0, 0, right? So now from here we can check for, because it is given in terms of min terms and other possible combinations. So F will be the D1, D1, D4 and D7 dash. So you can write it X0, X1 and X2 form also, right? So here it is in not in the correct form because it is in short X2, X1. Here it is the other one. So it is wrong. Now it is a not possible combination. Now we have to check the for min terms. So min terms we need to check where it is 1 because it is given in sum of product form. So it where it is 1 we have to write it that only, not in a product of sum form, right? If it is written in the capital M, then it can be correct. But here it is written in the min terms only. So summation M, what are the here where it is 1 at 0th We can write it directly 0, and where place the other 0? It is 2, then 3, 2, 3. Where the other places where it is 1, that is 5 and 6, right? 5 and 6. These are the possible minterms where the output are 1. So 0, here it is 2, here it is 3, it is a 5 and it is a 6. Okay, so option 2 is the correct answer from here. Okay, I hope you understand this. So have you got this question, or you are having any doubt? Hello. Okay, I hope you understand this. So okay, these are the questions for this week video lectures. So total 22 questions are there. Okay, so if you have now any doubt, you can ask it. Otherwise, we can close the session. Anyone of have any doubt? You can ask questions now. Otherwise, we can close the session. Yeah. Okay. Yeah. Thank you. Thank you, everyone. Thank you for joining the session. Yeah. If you don't have any doubt, you can. Okay. Yeah. Yeah. Okay. Okay. Then you don't have any doubt, so we can close the session. Okay. Okay. Thank you, everyone. Thank you for joining. We will meet to the next class. Yeah. Now class is completed. Okay. Thank you, everyone. Thank you for joining.